Hello?
Hi Josh, good
Hi,
afternoon, how are you?
I'm good, Dr. Pilkington. Good afternoon. Just checking to see if everything works. You can hear me okay and all that?
Yeah, perfectly, and if you want to try sharing your screen, go ahead.
Okay, great. I'm gonna try to share my screen from a different computer and use
Okay,
webcam from a laptop. So I'm just gonna see
no
if
problem.
I can
Yeah,
do that
go
here.
ahead, no worries.
Okay. Hi there.
Yeah, looking good.
Okay. And we'll get the presentation going.
Mhm. Yeah,
Nice. Okay.
just,
Um,
yeah, just need to stick it. Yeah, well, it looks good. And you found your laser pointer.
yes.
Perfect. Yeah, looks all good.
Great. Great.
Perfect. Okay, I'm going to turn my cam off. I am here, so if you have any questions, just feel free to ask. We've got another 10 minutes before the
Okay.
rest of the committee shuts. Dr. Metalinos is already online, so we just wait for the rest of your committee members and your supervisor, and then we should be good to go.
Okay. Sounds good. Thank you.
Okay, you're welcome.
Hey, Dr. Delamere.
Hello, how are you?
I'm good. How are you doing?
Pretty good.
That's good. Hey, Dr. Melinos.
Or Josh.
Good afternoon, Professors Nikonov, Messenger, and Lemaire. I think we're
Hello.
just waiting. Hi, I think we're just waiting for Professor Van der Est now.
Okay.
So hopefully he hasn't forgotten.
Melanie, just because we have a few minutes, I spoke to Irene about the pump, and the pump is sitting with customs right now for a week, and Irene is trying to press the broker to move it faster.
Okay.
So because Anton is leaving on 25th, and there are a few crystals that he has to do before he goes, because if he's gone, like, we will not be able to do it.
Well, we have been in touch with Oxford. We have been pushing Oxford to get moving with the pump, and I was aware that it should be shipped this week.
It is in Canada. It is in Canada.
Yes, I was aware of that, but that's good. I mean, Oxford had said we should expect it this week, so fingers crossed. They can get it to us.
Okay, so Art is here now.
Hello, Professor Meta. Hello, Professor
Hello.
Van der Est. Thank you, everybody, for coming today to Josh's candidacy exam. And Josh, he's set up. I think everything is okay.
Yep, seems good.
Everybody's connections are okay. So just a few words about the candidacy exam before we begin. So Josh, you have about 25 minutes to give us an overview of your proposal. Don't worry if you should lose your connection or if you need a few extra minutes, it's fine. You can have the time you need. After you have given us your presentation, I'll ask if anybody would like a break, and if anybody likes a break, we'll break for 5 minutes. If not, we'll continue on, and there'll be 2 rounds of questions. We'll start with your internal external examiner, which will be Professor Metalinos. And the first round of questions will be about 15 minutes. So we'll go Professor Metalinos, Professor Lemaire, Professor Van der Est, and finally your supervisor is also permitted to ask questions, so he can ask or ask you to clarify anything. And if I have 1 or 2 questions, I'm also allowed to ask as the chair. So that'll be the first round, so around 15 minutes, and then there'll be a second shorter round of questions in the same order, and about 10 minutes each. Then once we finish the questions, you'll be asked to leave the room, and we will ask Professor Nikonov to speak on your behalf, so he'll be able to make some comments about your progress, the candidacy proposal, etc. Then he will be asked to leave the room, and then the committee will deliberate, and they will come to a decision as to whether or not they feel that you have passed this candidacy exam, and then we'll call you back, you and your supervisor back, and we'll convey the results. Is that clear, Josh? Do you need any other explanation?
No, thank you. That sounds good.
Okay. So if the committee is all good and you're good, Josh, then we will start, and we're looking forward to hearing your candidacy proposal, which is based on the synthesis of SF5 minor substituted ligands for applications in transition metal catalysis. So Josh, the floor is all yours.
All right. Thank you, Dr. Pilkington, for the introduction and the explanation. Today I'll be talking about the synthesis of SF5 substituted ligands for applications in transition metal catalysis. And to begin, I just wanted to kind of speak on, in general terms, on the function of functional groups. So as chemists, we are intimately familiar with how functional groups can affect molecules, act as handles for reactivity, affect polymeric and material substances. And you can almost see functional groups as the paint in our palette if we were artists. And using different colors or using different functional groups, we can create beautiful images or molecules in this case with very specific reactivity. And it behooves us to ensure that we use all the different hues and tones available to us, and even those that are sometimes more niche and not widely used, they still have very interesting applications, and it's worthwhile to investigate these more out of the way functional groups. One such quite niche functional group is the sulfur pentafluoride group, SF5. So typically relegated to the domains of niche fluorine chemistry. The SF5 has this beautiful octahedral structure here with our standard 90-degree angles between all bonds, and the central sulfur surrounded by the wreath of 5 fluorine atoms as shown in this scheme. The electronics are probably the strongest point to begin here when describing the SF5, the most important point. Obviously, fluorine being the most electronegative atom, the SF5 is quite powerful in its ability to draw electron density towards itself and polarize molecules. We can use the Hammett parameters to more qualitatively define this ability to to draw electron density towards itself. And we see here in the comparison of benzoic acid or the aniline cation substituted with sulfur pentafluoride and triphenyl fluorine. Trifluoromethyl. We can see the improvement here in the sigma p Hammett parameter, and how this is able to better stabilize the acid association constant of the benzoic acid. Um, in general, the SF5 is kind of seen as a super trifluoromethyl group. So it's a bigger than the trifluoromethyl group. It's more electron withdrawing than the trifluoromethyl group. We can even see in terms of its inductive and its resonance Hammett parameters. We see here that it is a more powerful inductive withdrawer than trifluoromethyl. However, the resonance effects are fairly comparable. Now, the pKa, which we're all more familiar with, is actually almost on the level of a nitro group in terms of its electron withdrawing capacity. Um, and in terms of the dipole moment, here we see that compared to the trifluoromethyl again, the SF5 here is more powerful at polarizing these molecules with the higher debye amount here. So moving on to the sterics and the physiochemical properties. In this electrostatic potential map, we see here that the octahedral geometry is obviously is a much larger structure here than a trifluoromethyl. In terms of the atomic volume, we do see a increase. These are just the sulfur pentafluoral benzene and the trifluoromethyl benzene compounds. We see that this is bulkier, and it results in more dense species. Um, More accurately defined, the volume of the SF5 group is slightly smaller than the terp-butyl group in terms of its volume here in angstroms cubed. Still much more significantly larger though than the trifluoromethyl. So this actually is where things get quite interesting now, because we have a functional group that is very electron withdrawing, very polarizing, but it's also quite large, right? And you can see here it has a large surface area in terms of its electrostatic potential. So this makes it actually quite lipophilic. And lipophilicity and strong polarizations are typically not things that are found together in the same functional group. They're kind of counteractive. Usually stronger, smaller, more polar compounds are, or these small polar compounds are less lipophilic, but this is a very polar compound that is actually quite lipophilic. And we can define our lipophilicity using the Hansch lipophilicity constant. It's just denoted as pi here, but we can see that the lipophilicity approaches the terp-butyl group in terms of its ability, which is much more increased than the than like a nitro group, which is a similar electron withdrawing potential, but nowhere near the amount of lipophilicity. Um, Now, this is uh, this is very interesting for pharmaceutical applications because we have here a functional group that is very polarizing, very electron withdrawing, but also lipophilic, and that would allow it to now permeate fatty membranes and act as a more effective drug delivery system. And that is one application that the SF5 group has really found in the past few decades is just the improvement of certain pharmaceutical agents just by simply installing the SF5 where perhaps a trifluoromethyl existed previously. So moving on to its stability, the SF5 group is quite stable. You can see here that it's stable in concentrated boiling sulfuric acid, and on the other extreme end of the scale, sodium hydroxide, boiling base, we have no hydrolysis occurring. The trifluoromethyl group would undergo hydrolysis nearly immediately under both of these conditions. It's also quite thermally stable. At 400 degrees Celsius, the pentafluoral sulfonyl benzene did not decompose under high temperatures, and we can see here that this now opens us up to many different routes of post SF5 installation reactivity, where we can do our coupling reactions. We can do strong oxidative or reducing conditions, and our SF5 isn't a point of failure in these environments. And I won't go through detail of all these reactions, but these have all been reported in the past, and it basically means that we can install our SF5 group, and then we can do additional transformations without worrying about any kind of hydrolysis or cleavage of the SF5. So all this stability has, as I said, made it excellent for pharmaceuticals. Um, Anti-malaria drugs specifically have been found to maintain their excellent selectivity against the malaria parasite, but now have increased bioavailability and increased effectiveness due to the more lipophilic SF5 installed in this drug here called mefloquine. The same is true also for this triazolopyrimidine-based inhibitor. This doesn't have a name yet, but it's also a active species in fighting against the malaria parasite. It inhibits some of the activity of the crucial enzymes for the malaria species. Agrochemically, we also have a similar story. Installing SF5 groups into the herbicide trifluralin have resulted in increased activity against crabgrass and other herbicides, other weeds, without broadening the selectivity, and it's maintained its effectiveness. Optoelectronically, we also see this improvement. Because the SF5 group is more polar, liquid crystals which have replaced CF3 with SF5 have had improved performance, and this is just due to the increased dielectric anisotropy for the SF5 here compared to the CF3. So everything seems maybe too good to be true here, and it kind of is. There is a catch, and that is the Achilles heel of the SF5, the synthetic accessibility. So historically, SF5 has SF5 synthesis has suffered from several major drawbacks, specifically low yields, costly and or dangerous reagents, limited substrate scopes, and difficult to handle gas reagents. The first reported synthesis of SF5 was by Shepard, who reported the synthesis of the aryl derivative in the 1960s. And he used this diaryl disulfide along with 8 equivalents of the very expensive silver fluoride in boiling Freon to obtain only a 9% yield of the benzene, benzene SF5 here. 4 decades later, the Janison group reported a new synthetic method, which wasn't significantly better. They had to employ the explosive xenon fluoride, but they were able to obtain 25% of the pentafluorosulfonylbenzene. Now, the same year, Philip proposed the following. He didn't improve the safety or the cost of these reagents much. He used fluorine gas, which we know is very pyrophoric and dangerous, difficult to handle, but he could obtain higher yields. However, his substrate scope was quite limited, only to the nitro substituted diaryl disulfides. So not much work, as you can see, from the 1960s all the way till 2000. Not much work was done really in terms of improving the synthetic protocol, and this is the major reason why SF5 chemistry hasn't really caught on, despite these intriguing aspects of high lipophilicity and strong polarizations. It hasn't really gone anywhere too much. However, recent synthetic protocols have really started to change things up. Modern methods, like the 2012 method by Yamamoto, have allowed for a practical and economical two-step procedure. So the first step is an oxidative fluorination, still sticking to the diaryl disulfides as previously used. The Yamamoto group was able to drastically expand the substrate scope to those shown here, and using chlorine gas along with potassium fluoride, they are able to obtain this first step intermediate in good yields of the tetrafluorosulfonyl chloride here. Now, the second step was a chlorine-fluorine exchange. Using a cheap fluorinating reagent like zinc fluoride, they're able to obtain the SF5 derivative now in pretty good yields. So this now really began to open up the doors for SF5 chemistry. And further developments were made by the Pitts group recently now in 2019, who again democratized SF5 chemistry with the use of TCI-CA as a fluorinating reagent and a replacement to Yamamoto's step 1. TCI-CA is a trichloroisocyanuric acid, and the Pitts group showed that with this extremely cheap chlorinating and oxidizing reagent is actually used as a pool cleaner and produced like many tons, thousands of tons per year. This chlorinating reagent with 18 equivalents and still with the potassium fluoride, they could obtain the step 1 intermediate in fairly good yields. Not only was the aryl diaryl disulfide substrate scope expanded, but this also was applicable to heterocycles. So pyridines, pyrimidines, indoles, triazines, all were well tolerated, and we were able to get SF5 derivatized heterocycles through the Pitts method. So to kind of summarize some of these really interesting modern methods of SF5 chemistry, we have our step 1, which could be done either by the Yamamoto method using chlorine gas or by the Pitts using trichloroisocyanuric acid. And then from there, we can do a step 2 chlorine-fluorine exchange to obtain our SF5 aryl derivative. Now, many step 2 chlorine-fluorine exchange protocols have come out in the recent years. Just recently, a few months ago, the Shibata group developed the use of silver tetrafluoroborane, and they all have various pros and cons. Some work better for heterocycles, some work better for aryl groups, different substituents, and so on. But now currently there exists this gap in a way. And the gap is that there has been massive developments in terms of modern synthetic protocols that allow for accessibility to SF5 aryl derivatives, but the applications of these compounds is still relegated only to niche pharmaceutical applications, optoelectric, and agrochemical. So my proposal now for as part of my candidacy exam would be to include this SF5 group into transition metal catalysis. And I propose the synthesis of SF5 substituted phosphine ligands to create these electron deficient, highly active catalysts. And they're believed to be high performing due to their stabilization of lower oxidation states, the enhanced metal Lewis acidity, and the increased selectivity via the steric bulk of the SF5. So what I'm trying to accomplish here is essentially an optimization of the ligand acceleration effect. And the ligand acceleration effect is a general concept in catalysis where the reaction rate of an already existing catalytic transformation can be improved with the modification of a ligand. And this has been shown quite clearly by the Fagnot group in 2010, where they use this biaryl Buchwald type S-phos ligand, or they use four of these four derivatives of the S-phos ligand to show how in direct arylations the electron withdrawing nature of the ligand has an effect on the catalytic turnover and catalytic activity. And we see this quite clearly in the yields and reaction rates here. Looking only at the S-phos ligand, we see barely any activity. And as we increase in the electron withdrawing nature of the ligand, electron poor substituents here, we have dramatic increases in the yield and reaction rates. And as I've previously shown, SF5 is a super trifluoromethyl group, so I expect it to result in higher yields, faster reactivity, and better optimization of these processes. So electron deficient phosphine ligands are not new. And there's actually quite a lot of work done here. Pollock et al. Has recently reviewed the role of electron-deficient fluoroaryl phosphine ligands in homogeneous catalysis. Their conclusion was that the importance of this type of ligand is growing. And they comprehensively looked through the past decades of literature and showed all these different applications, catalytic applications, in which electron-poor ligands have outperformed their electron-rich counterparts. Some noteworthy kind of structural motifs that we observe are the polyphosphine type and the triaryl, and then a mix of aryl and other substituents shown here. But in all of these cases, we see dramatic increases in reactivity and antioselectivity in some cases as well, and reaction rates with our more electron deficient derivatives. So why is it then? Why is it that we have this increase in ligand acceleration effect and with our palladium direct, or with our, why do we have a ligand acceleration effect with our electron poor phosphines? Well, it has to do, well, we can look at the an example here of a direct aerolation and my hypothetical palladium complex shown here. And in this direct aerolation, we proceed through the typical oxidative addition, transmetallation, reductive elimination step, but we proceed through a very important concerted metallation deprotonation, a CMD process. And I can show a scheme here in which we have our oxidative addition and then our substitution with a carbonate here to form this intermediate. And then now, as we have our approach of a simple arene, we have that activation of the hydrogen-carbon bond and the approach of the palladium to the carbon sp2 hybridized center. Now, this interaction here specifically has been reported to be dramatically stabilized by the presence of electron withdrawing aryl substituents on the phosphine ligand. In addition to this, as this is typically the rate determining step, as we improve the stability of this transition state, we improve our rates of catalytic reaction. Now, as for our reductive elimination, this would also be stabilized by the electron poor phosphine, as there is not as much electron density on this on the metal center. The return to a low oxidation state would be favored. Counteracting this, of course, would be the oxidative addition being destabilized, but depending on the catalytic application, it seems that where you have reductive elimination as more of a barrier, it does improve the situation. So my goal then primarily would be synthesis, and this will be the first reported synthesis, by the way, as there hasn't not been a transition metal catalyst employing SF5. We would then synthesize SF5 derived phosphines. And my main target would be the synthesis of a 4-bromophenyl sulfur pentafluoride, which I would then use as a nexus to access various phosphine ligands. My proposed synthetic route involves the use of cheap and readily available bromobenzene, reacting with chlorosulfuric acid to make the 4-bromobenzene sulfonyl chloride. To this, I would then do a reduction with phosphorus to obtain the bromobenzene thiol, and then using the established procedure of oxidation with iodine, I could obtain my brominated diaryl disulfide. An exemplary reaction here using the Pitts procedure, and then the Yamamoto method of chlorine-fluorine exchange with zinc fluoride. I should expect to obtain the 4-bromophenyl sulfur pentafluoride shown here. Other substituted SF5s could also be obtained via the following. If I have my diaryl disulfide, I can then obtain the SF5 using the established procedure, and then do an electrophilic aromatic substitution with N-bromosuccinimide to get a meta positioned SF5. Although for my purposes, where I'm trying to create these very electron poor ligands and reduce electron density on the phosphine, the 4-position SF5 would be preferable. But it's just if I wanted to play with steric interactions here, I could create something like this. Now with this bromo pentafluoride, sulfur pentafluoride, I can then undergo a Grignard reaction where I would obtain the species here. And from here, we can then do nucleophilic substitution to obtain, for example, the Buchwald ligand here. And all I would need was just the chlorinated phosphine ligands. The same can be shown here for this polyphosphine ligand, where I could obtain the 1,2-bis diphenylphosphinoethane or the propane derivative shown here. This would also work well for asymmetric ligands, so like the Naiori binap style ligand could also be obtained. And there has been reported improvements in electron withdrawing phosphines in the asymmetric 1,4 hydrogenations. So electron withdrawing chiral ligands may actually have a good application that's worthy of investigation as well. We can also just form the simple triaryl phosphine through the halogen exchange step here, and then using butyllithium along with phosphine trithoxyphosphine, we could obtain this product as well. So, in conclusion, SF5 is a powerful electron withdrawing group that is chemically and thermally stable, bulky, and polar. The recently developed synthetic protocols have dramatically improved accessibility to this exotic group, yet no applications in transition metal catalysis have been attempted. SF5 functionalized phosphine ligands are expected to dramatically increase yields and reaction rates for cross-coupling reactions, and the proposed synthetic route is expected to yield a wide variety of mono and polyphosphine electron poor ligands, which should be suitable for catalysis. So with that, I'd like to bring my presentation to a close, and thank you all for joining me here, and open the floor to any questions as well. Thank you.
Thank you so much, Josh, for an interesting presentation. Would anybody like a few minutes break? Let me know. quiet. No, everybody's good.
Yeah, I'm fine to continue.
Okay, you're good, Josh. Everything's
Yep.
good with you.
Yep, good.
Okay. Then I will start the round of questions, and I will open the floor up to Professor Metalinos to ask his first round of questions. Thank you.
Thanks, Dr. Pilkington. Josh, very nice proposal, very nice presentation. Really intriguing, simple idea that I think you can take in many different directions. So I've got some, some detailed questions, but also some general questions about this group because I don't know very much about it. And I'd like to know more, especially based on what you've discussed. So first of all, if we go back to, I can't remember which slide it was that you presented today, but it might have been the second one where you have a picture of an SF5 substituent with the various bond distances. There we go, that's the one. So one of the things that makes trifluoromethyl a particularly useful substituent, apart from what you already described, being electrolyte drying and lipophilic and suitable for pharmaceutical applications, is the fact that it serves as a tag, right, for functional group tag as well. So you can do, for example, things like fluorine 19 and MR spectroscopy on it. And in which case, if you do F19 chemistry, assuming you don't have another, spin active nucleus nearby, you get a singlet, right? But because you have different bond lengths in SF5, what would you see in this particular substituent if you were to run an F19 spectrum of that compound, of that substituent specifically?
So F19 NMR of the SF5 group should give you, I believe, you'd see a doublet for the 4 equivalent equatorial phosphines or fluorines, and for this one axial fluorine, you would expect to see a pentet. Quintet. Sorry.
Yeah.
Quintet.
Right. Okay, so they are distinctly different, and you can see that also by an MR. Okay,
yes,
that's quite interesting. Okay, they don't move around in any way. Okay, well, at least
rotation may be around the equatorial, but
you don't see them shifting positions like you would in like something trigonal bipyramidal or something like that.
No.
So that's interesting that you can see that difference. So that's interesting because you might be able to get a tag sort of on the molecule and see different mixtures of compounds by having different sets of signals at different locations. Does the fluorine coupling extend to if you're making aryl substituted ligands like you are? Do you think the coupling to fluorine would extend to the ipso carbon atom?
I think it should. Maybe you would see some satellites on the equatorial peaks just from the carbon 13 at the ipso atom of the aryl. And I believe the coupling, well, at least the F19 coupling is about 150 hertz between the fluorines there. But yeah, I think you would see some excitation. Yeah.
Okay, well that's interesting. That was just for my own curiosity looking at that substituent. Okay, I think let's go to slide 5 of your presentation, where again you have some comparisons between this particular group and trifluoromethyl. And
was it this one, or maybe another one before it?
Yeah, let's see. Right. So one of the things with CF3 that you mentioned may not be this slide specifically, but that's okay. That you mentioned is that SF5 seems to be quite a bit more stable, right? In a lot of circumstances, at least in very acidic and very basic conditions, it's more stable. SF5 is more stable than CF3. But the one thing about CF3 is you can't really do chemistry at that carbon atom very easily, right? But with SF5, the procedure that you're using to make that particular group goes through a pentasubstituted, well, I guess you have 1 chlorine atom, right? At some point, and four fluorines.
Yes.
And then that you substitute it out by the modern method that you already discussed.
Yeah.
So that intermediate, where you have a single chlorine atom, or even if you have all 5 fluorine atoms there, can you do substitution at sulfur as a competing reaction? Especially if you have a chlorine atom. Has anyone ever tried that? Has anyone ever demonstrated that?
So it seems that once you have this this SF5, it kind of the sheer bulk of
Right.
the fluorines around that sulfur really do make it inert to most types of reactivity, and it
Okay.
even protects the ipsocarbon as well because it's just so much electron density
So big,
around.
right.
Yeah.
Go to that slide. I think it's slide 10, where you have
Yes.
the chlorinated intermediate. So does that also apply to the to that middle structure there? Does that also apply there? You can't do substitution at that position at sulfur?
So with the tetrafluoro sulfur chlorine, I guess it would be more, well, no, it should still be inert because you have those same protection, the steric protection of the four fluorines and the chlorine around it.
Right. Well, I guess it depends on where the chlorine atom is too, right? Where do you think is the chlorine atom in the apical position here or not?
I think axial, yeah, for sure. I don't,
Yeah,
yeah,
okay,
definitely,
so
definitely.
yeah,
I think there's crystal structures as well that confirm that. It's
that
not
confirm
inequit,
that.
yeah, yeah.
And in solution, so in the case of SF4Cl, what would you see in the fluorine 19 NMR spectrum?
You would just see a singlet, I
Yeah,
believe.
right.
Yeah,
So there's verification of that, do you know?
Actually,
Solution versus solid state?
I'm actually not sure. I know, yeah, I wasn't too familiar with the NMR spectra for the intermediate, unfortunately. But but I expect it to be a singlet.
Okay,
Yeah.
I'm just asking just as a thought experiment because I don't know myself. Just asking out of my own curiosity.
Right.
Okay, and one other thing that's related to this is the fact that you have some examples, including on this slide, of high deficient aromatics like the pyridine substituent on the right, where again you're hoping for stability there. Can the SF5 group act as a leaving group by itself, where the whole thing is displaced? For example, by nucleophilic aromatic substitution, like in a pyridine or another pi deficient aromatic system, is there any evidence that that's possible? So, in other words, can it behave like a glorified halide?
I don't think so. I haven't seen any evidence of it. Just like acting as a leaving group and then doing an SN2 substitution at the carbon there. I haven't seen anything like that. It seems like once you install the SF5 group, you're kind of stuck with it.
You're stuck with it.
Yeah, even like metabolically in these pharmaceutical papers, like it seems that there is no metabolites that can break down the SF5 even, or it just seems to be there. Yeah, it seems quite stable, and it doesn't act as a leaving group either. Yeah.
Okay, interesting. All right, what else can we go here? Don't know where to start. Let's look at your Grignard reaction.
Okay.
I think towards the end, since you have the slides up here, though it's also in your proposal, where you discuss, right, a potential way to access these compounds via, direct preparation of the Grignard reagent. So you don't have to worry so much about it because you've already, settled that the Grignard reagent is going to attack, the SF5 substituent by itself. That's inert, so we don't have to worry about that. Don't have to worry about the SF5 group leaving potentially, where the SF5 substituent act as a leaving group in that respect. So that's fine.
Well, can I actually? Sorry, I should let you finish. But one thing is that it is quite stable, but N-butyllithium it decomposes with N-butyllithium. So strong enough base, it will actually be a problem. But with tert-butyllithium, it is stable still. So, but yeah, it is. I guess it is something to watch out for there then.
Okay, so then what happens with N-butyllithium? What does it turn into?
I believe it substitutes the. So you do have cleavage of the carbon sulfur bond.
The carbon sulfur bond. Okay.
Yeah, and we. I'm not actually sure. Like I'd have to speculate because they didn't characterize the decomposition products when the reactions failed with N-butyllithium.
Do you get an aerolithium? Does it generate an aerolithium if you react phenyl SF5 with butyllithium? Is that what happens?
Yeah, I think. Well, yeah, I think maybe you would because I'm not sure because they didn't they couldn't characterize these decomposition products in the papers where they tried N-butyllithium. But I think it may attack the
I guess the question is, what do they get as the product? What's the product?
What's the product with N-butyllithium? It might be and it may be the ring with the like a lithiated ring, and then uh, SF5 would then maybe attached to the I don't know, maybe attached to the butyl group, or
Okay. Well,
yeah.
that's something to look into because
Okay.
so basically what you're telling me is that there is a potential for the sulfur for SF5 to be reactive under certain conditions, right?
Yeah, yeah, with
Which is maybe
very
why you
strong
got
base.
at least Grignard may be better here. But that's interesting because there it is known, for example, I believe that toluene sulfoxides, okay, so sulfoxides with toluene substituents on them, especially with another aryl group on them, you can do sulfur lithium exchange with tert-butyllithium in those cases. That's a known reaction. So tert-butyllithium plus certain chiral sulfoxides, toluene chiral sulfoxides can be displaced, and you get the aryl lithium species as a byproduct, and you get some, I guess, some, tert-butyl sulfoxide as the byproduct coming off. So maybe this is something that you can do. That's potentially actually a selling point of this chemistry, because you might be able to convert it to something else afterwards, right? Not just be stuck with it. So it's something that you might want to look into.
Okay.
For that. Okay. Sorry, I got a bit off track because didn't expect you to say that's reactive.
Sorry. Yeah.
Okay, that's fine. No, that's okay. That's okay. Okay. Where else can I go here? So you have how much time do I got? I got about I think 5 minutes or so. So let's see.
Yeah, you've got about 7 minutes. So
about 7 minutes?
Fine. Yeah, go for it.
Okay, thank you. All right. All right. So here you have a couple of examples where you're using T-butyl, right, to do an exchange here of the iodide, and you make your phosphine. That way with triethylphosphite, and you get your trisubstituted phosphine in the right-hand side there. You also have derivatives above where you have aryl substituents exclusively, or you have mixed alkyl aryl substituents, like in the middle case there.
Yes.
So my question to you is, when I look at your proposal, you do not have a you have a lot of equipment listed, but you don't have a glove box listed.
Right.
Okay. So do you expect these ligands to be air stable, or do you expect some of them to not be air stable? Which ones do you think will be air stable? Which ones do you think will not be air stable? Let's start there.
So
because it's a practical issue, right?
Right. So I think that, like, for example, we'll start with the simple triaryl phosphine. Eventually it will oxidize phosphorus 5. However, I expect it to be slow. I expect it to be a slow oxidation just due to the electron withdrawing nature of the aryl groups. With the other phosphine ligands, oxidation is a risk still. So, like, yes, okay, to kind of go back to the glove box, like, yes, I think this would all have to be it would make things easier to have everything done at least on a Schlenk line or in a glove box. So yes, I think that is I'm realizing that's a mistake, and I should have a glove box, at least a small one, for these kinds of reactions, maybe.
It's not a mistake. I mean, people were doing this kind of chemistry before people had glove boxes all over the place, right?
Oh, true.
But the question is, do you know how okay, you already addressed the point of dealing with, Schlenk conditions and isolation, and how do you do isolations like that so that you can put things in a vial without having to use special equipment. But from a practical perspective, I've said this before, like the difference between organic chemists and inorganic chemists is that inorganic chemists have less problem of isolating products that are unstable. Whereas organic chemists really don't like doing that. They like to make things that are unstable as intermediates, but we don't like isolating them when they're unstable, right? Like they play with things in the open air because we're lazy or something. So, so the question is, how would you do you know of a method, especially for the alkyl derivatives, which might be more prone to oxidation, right? Because they don't have all these electron withdrawing groups on the phosphorus. How would you protect? Do you know of any of the methods that you can protect the phosphine from oxidation? As some other intermediate that you can then displace. And there actually are some commercial ligands that use that trick, including, if I'm not mistaken, some of those Bookwald ligands that you've discussed.
So they protect them from. So maybe could you use like a selenium or something, like a different transition, a different. No, but then that would be hard to get off.
To me, something that's something else in the oxygen series. Discussing.
So yeah, that's what I was thinking. Selenium, yeah, like something else in the oxygen series that maybe you could take that off later.
Okay.
Mhm.
That is a common trick, actually.
It is. Okay. Okay. Yeah.
It is. Yeah, that's
Okay.
your mind went to the right place.
Okay.
Phosphine sulfides also are very easy to make. All you have to
Sulfides,
do
right?
is throw
Sulfides.
elemental sulfur at it, and then it will make the phosphine sulfide. Do you know how to reduce them back to the phosphine though?
To reduce them back to the phosphine, something that's not strong enough to do substitution. Could you just use? I'm sorry, give me a minute here to think.
It's actually low-tech, second-year organic chemistry, probably. I'm going to think in that.
Easy, something easy, an easy reducing agent.
Relatively low-tech, yeah.
Oh, I was thinking I was gonna say like cyclopentadienyl cobalt or something like this.
Yeah, maybe that's too fancy.
Too fancy? Okay, low tech.
People have used things like rainy nickel. Rainy nickel seems to do that.
Okay, rainy nickel.
As long as we have other sensitive groups that can be reduced.
Okay.
There's other ways to do it. For example, borane.
Oh, okay. Yeah, borane hydride.
Attack the lone pair with borane and then knock it off. And there's another even easier trick that's I've seen in the literature, and including in commercially available ligands. I think even triterbutyl phosphine itself is sold as a particular protected version. Think of amines. There's your hint.
Oh, okay. Yeah. So, like DMAP or
not DMAP. How do you protect amines?
You can use like Bach or something.
Okay, but not with tertiary amines, you can't, right? These are
tertiary. Not with tertiary, right? Not with tertiary.
So even simpler. Think really simple.
Protecting amines.
Tertiary amines, yeah. Drugs are often formulated that way for that reason.
Protective amine with. I don't know. I'm not sure on this one.
Just acid. What if you use acid?
Just acid to protect. Oh, to form the cation, or like the.
What would you form if you used a strong enough acid?
You would form like the ammonium salt, like we were talking with amines.
So what'd you get in these cases?
In this case, you would form like phosphonium salts.
Yep.
Oh, okay, so then phosphonium salts can then be reduced later.
Or just treat it with base to free up, right?
Okay. So like sodium.
Yeah, you can use anything. You can even use T-bule or bule if you want. But you can isolate the phosphonium salt depending on the counter. And usually HBF4 is used for something like that. I believe in the case of triterbutyl phosphine.
Okay.
And it's air stable. You can open it. You can weigh it out as a white solid or whatever it is. Right. And then you can treat it with a base, and there's your free phosphine.
That's useful.
Okay, so that's also another thing that you can do. Tricks of the trade, right? That you avoid the problem of air sensitivity. Okay. All right. I think cool. I'll quit there for now.
Perfect timing. Yes, thank you very much. So Professor Lemaire, would you like to ask your questions to Josh?
Sure. There I am. Hi, Josh.
Hey.
So I enjoyed your reading your proposal, and your presentation clarified quite a few things for me. Now, so when I read your proposal, I was reminded I was on Anton's committee, so I was at his defense, and one of the things that he impressed upon me in his thesis is the field is sort of moving away from heavy transition metal catalysis, because of issues with scarcity of metals and so on, and environmental issues and so on. So you're proposing new palladium catalysts. Is that, do we need more of those? How would you defend that? I'm just playing devil's advocate.
Sure. So what we've seen, it's just true that the field is moving away from heavy metals, or at least people popularize the use of alternatives to transition metals a lot these days. And this proposal is, palladium, like ancient technology. But what really struck me with this type of catalysis is like I've said in the presentation, higher yields and selectivities and better performance, but also significantly decreased catalytic loads. In fact, like 0.01%, where previously 5% was needed. And with that very reduced catalytic load, you could still get you could outperform like 5% load catalytic loads with traditional non-electron poor phosphine ligands. So that would be my defense, would just be that in terms of, if we're looking at cost basis here, um, the dramatic reduction of catalytic load is quite viable. Now, in addition to this, there's no need for replacement of pre-existing chemical industrial infrastructure. We could still use our current setups, and now just improve on activity and yields along the way.
Sure. Okay. So what about adapting these ligands to other transition elements?
Yeah. So electron poor phosphines have shown great reactivity with the rhodium transition metal as well, for applications in 1,4 asymmetric hydrogenations. Um, they showed that like the binap ligand could do some chiral reactions with rhodium. So it'd typically be relegated to late transition metals in terms of my metal selection.
Okay, so it's not like you'd be going to like iron or cobalt or anything like that with these
No.
systems.
Yeah,
Okay.
more focused on these.
Now, the other thing that kind of I was thinking about as I read your proposal was you're proposing to make just to make your 4-bromo substituted precursors. How many? I think it's 4 or 5 steps.
Yes.
Yeah, and some of these reagents I'm not too familiar with. Are they expensive?
So looking at the costs, bromine is or bromobenzene is extremely cheap. So is the chlorosulfonic acid and sodium salt, of course. It's actually quite cheap. Everything is quite cheap. I think maybe like truly, I don't see any issues with cost, even though it's
Okay.
multiple steps. These could be ordered on like many hundreds of gram scale, and you should be able to obtain this species. Perhaps the zinc fluoride may be like the most offending here. But to buy any of these intermediates is much more expensive. Like to buy a diaryl dibrom disulfide is this species specifically is like $2,000 a gram. So it really works out well to
Okay.
start from the dirt cheap bromobenzene.
And the other thing that I worried about a little bit
Yeah.
was like your lab is going to be a toxic waste dump of fluorine, organofluorine waste, and so on. So
Yeah.
have you thought about that a little bit? Like
Yeah.
again, in the field, it seems like that people are moving towards kind of sustainable chemistry and green chemistry, and I don't see a lot. Like again, how would you defend my argument that you're going to be kind of a toxic waste dump in your research?
Um, So the product itself, the SF5, um, is actually not quite not toxic at all. The LD50 is quite high, about 2,000 like milligrams per kilogram. And it's really only the intermediate, I believe, that is somewhat dangerous and like malodorous. But the SF5 itself seems to be not that toxic, and even in terms of like mutagenicity, like that it could induce, it's fairly safe there. Like they did a lot of toxicology screening on these aerial species just due to their implications in pharmaceuticals. And the yields of all of these transformations, I don't have them specifically for these, but in terms of comparable chemistry, the yields are quite high. So I'm expecting to not have quite a lot of side reactions and side products that need to be disposed of. But it is kind of that it is a sulfur compound, so that is kind of unavoidable.
Mm-hmm.
It is not a super green process, but I believe it is quite atom economical in terms of its use of reducing agents and additives here.
Okay.
Yeah.
So in your proposal, I know that kind of the thrust is synthesis of the ligands. So you don't really talk a lot about the catalysis. I think you only gave like one example in the proposal of one typical reaction that you would look at.
Yeah.
So let's talk like you showed us a catalytic cycle, and you said something about thank you, about the with these super electron withdrawing ligands that you're going to favor the final step, right? Reductive elimination.
Yep.
But you didn't really mention that what could be the potential problem is the oxidative addition.
Yep.
Right. So here's what scares me. You have very long synthesis to get to your ligand, right? Like to get to the precursor, then you have to make the ligands. And what if the oxidative addition doesn't go? What are you going to do?
So if we're assuming here that the oxidative addition doesn't work for that specific catalytic application that I described, and we can't access past that. Well, I believe in this case I would look into other catalytic applications. Like I have seen large ligand acceleration effects in quite a few other types of reactions, with different substrates, all very different substrates within these. So if I did attempt like that direct air relation that I mentioned in my proposal, and I couldn't get past that activation barrier of the oxidative addition, I would look to see if I could have improved catalytic effectiveness in a different application. Yeah.
Okay, like I guess maybe we could talk a little bit about oxidative addition. So
Okay.
what can you tell me about that mechanism?
So in this oxidative addition, we have approach of so this is a palladium zero, that is derived from the palladium 2 acetate that's reduced by the phosphine to form this palladium zero catalytic species. And then we have approach of the aryl halide, which undergoes an oxidative addition across the palladium to oxidize this to palladium 2. And we have essentially insertion of the palladium between the aryl and halide bond. But it is dependent on the ease at which you can access the palladium 2 oxidative state. And yes, having electron withdrawing ligands will restrict the ability to do this, just because it's already an electron deficient metal, and now you have to get into a +2 oxidation state. Like that is going to be a barrier for sure. But we've seen kind of in other applications that despite this being a barrier, the trade-off in terms of stabilization, the stabilization of other important rate determining steps in the catalytic cycle, that energy trade-off seems to be worth it in some applications. But it's an inescapable increase in activation energy, just by the nature of using a more electron deficient ligand.
Okay.
Yeah.
I guess I have a few other questions about phosphine metal, the phosphine metal bond, and orbital interactions. So you didn't really talk too much about this in your proposal. just, can you tell me a little bit about that? Like the different types of orbital interactions that you expect and what orbitals are involved in the different donor acceptor behaviors of these types of complexes?
So I expect this to be like an L-type ligand, essentially, where we're going to have a donation of the lone electron pair from the phosphine to the metal, and it's going to form a dative covalent bond, dative covalent sigma bond. However, the sigma interaction with the metal may be somewhat reduced just because this is a very electron poor phosphine. So I've seen in some papers where they actually struggle to coordinate phosphines to metals directly just because they're electron poor ligands. But they say just like premixing the ligand with the metal allows for like coordination before the addition of substrates and additives and everything. But yeah, sorry, I don't know if I answered the question, but yeah,
Yeah, that's part of it. But what
okay.
about pi character?
So there is
Like what kind of a ligand do we have within your system here? Do we have pi acceptor, pi donor?
we would have a bit of a sigma donor and a pi acceptor.
Okay, good. So
Yeah, pi
what's
acceptor.
the acceptor? What's the acceptor part?
So it would be the orthogonal like p orbitals that would overlap with the d orbitals that are in that are symmetry like agreed upon in terms of symmetry. And as you donate through the sigma bond, you'd have back donation to the phosphine from the occupied d orbitals of the metal.
So what type of orbital is the acceptor orbital on a phosphine?
I believe it would be a p orbital, like that, or
P orbital.
yeah, or like specifically it would be um I guess what type of orbital would be the acceptor on the phosphine is a question.
Yeah.
And p orbital is a bit too general, so I mean maybe like well like pz, px, py.
Like if you let's think of something simpler. Like if you have like a carbonyl.
Yeah.
What's the acceptor orbital on a
Uh,
carbonyl?
so it's a sp hybridized orbital for
No.
for the carbonyl. Like an anti-bonding orbital, right? Maybe
Yes.
that's
Yeah.
okay.
What
Sorry,
kind of
yeah.
so what kind of antibonding orbital
Oh,
is in a carbonyl?
yeah, it's a pi
But
star anti-bonding orbital.
yeah.
Yeah.
But with phosphine, like what if you have PF3, for example? What is the, and we know, is that a good strong pi acceptor?
No, I don't think so.
PF3 is, you don't think it's a strong
Or
pi?
I'm actually not sure, but I think it would. So the PF3 would be
You remember in the olden days, people used to think that in phosphine ligands, the acceptor was a d orbital,
right.
an empty d orbital on phosphorus, but that's been
Wasn't it?
debunked, right?
Yeah,
So
that's
do you
not it.
remember what kind of what the acceptor orbital is?
The, I think it was the oh jeez. It's not d orbital, and they're doing sigma bonding through the I guess like the hybridized orbital. So I would just say it's like the like and then the pi star is the higher energy unoccupied, like your LUMO. Oh. No, I'm actually not sure.
So between phosphorus and carbon, what kind of bond do you have?
Between phosphorus and carbon in the aryl
Yeah.
and the phosphorus, that's just like a covalent sigma bond there.
Right. So and that has electrons in it.
Yeah, two electron, two center.
What's the other component to that bond to that? So you have a bonding component, and what else do you have?
Oh, you have an anti-bonding component.
Sigma star antibonding.
Sigma star, right?
Right. That's the acceptor.
Oh, it's a sigma star. Okay.
In phosphine ligands.
Mm-hmm. The sigma
right.
Star.
So,
okay.
Anyway, that's I think my time's up for this round, so I'll save the rest of my questions for the next one.
Thank you very much.
Thank you.
Thanks, Josh. Thanks, Professor Lemaire. Professor van der Est, would you like to ask your questions?
Sure. So first of all, Josh, that was a very nice proposal. I really enjoyed reading it and delving into some inorganic chemistry, which I don't usually do, and so on. I'd also like to thank Dr. Lemaire for asking all my questions. But anyway, I'm going to follow up a little bit on something he asked. So, he talked about kind of what's the selling point for this, and in light of the fact that the field is going to, lighter metals and so on. But, I mean, really the comparison I would have liked to have seen would be between the fluorophosphine ligands and your sulfur pentafluoride. So is there a reaction with a fluorophosphine? So if you read the literature, the fluorophosphines, a few papers I kind of perused, they all say we get really high yields and it's all very efficient and so on because of the electron withdrawing effect of the fluorines and so on. So is there an example that doesn't work very well that you might expect to work well with the SF5? Right, because that's really the motivation for doing this.
Right.
And I kind of missed that, okay, here's the example of the one that, these things work well, but maybe not so well here. But if we could increase the electron withdrawing ability, it would work better and so on, right? So are you aware of any example like that?
So I think kind of with the arelations, I don't know if I'm really answering the question here, but like with these types of reactions, they've seen linear correlation between electron withdrawing ability and reactivity, and if these SF5 groups are as other tests have confirmed more powerful electron withdrawing species, then we should see an increase in activity specifically with like direct arelations, for example, if we can get past that oxidative addition barrier.
Sure.
Yeah.
But is the activity a problem with the other ones, right? So if it's already very, very good, then
right, why improve?
Room to improve, right?
So with electron deficient aryl species specifically, that's already a kind of a difficult process, just due to the lack of reactivity now between electron deficient aryls and the catalyst. But if we increase the Lewis acidity of our metal center, then we can maybe have some reactivity with like highly electron deficient aryls and get some coupling where there probably wasn't before.
Right. Okay, so that's something you probably should have stressed a little bit in the proposal, right? So here's a problematic case, and if we can increase the electron deficiency of the ligand, then maybe we can overcome that.
Okay. Yeah.
Let me see. So what factors, though, other than the electron deficiency of the ligand play a role in the activity here? Right. So there's some of your references have fairly detailed studies actually of exactly this mechanism.
So we're saying besides just that electron withdrawing nature of the phosphine, how else can these ligands affect the catalytic cycle, right? How do they improve?
In one of the papers, they showed an example actually where there's a very high electron deficiency in the ligand, but the catalyst doesn't work very well, right?
Right.
Because other factors.
I remember that. Yeah, and that paper specifically, it has to do with the difficulty in the coordination of the phosphine to the metal, and basically you'd have catalytic decomposition just due to the reduced sigma donating ability of the electron pore phosphine.
Yeah, so that's the stability of the catalyst itself, right? So that's one factor.
Right.
What do you expect that to be like for the SF5 ligands?
It'd be worse. It would be more difficult to coordinate to the metal center.
Right.
But I think with enough like premixing of ligand and catalyst before addition of substrate,
Right.
they did describe that if they threw everything together, like palladium acetate, ligand, substrates, additives, they didn't have any reactivity. But if they premixed these electron deficient ligands with the metal for even 10 minutes before addition of substrate, they would have better activity than before.
Sure.
So I expect there needs to be a kind of a preparatory step of ligand metal coordination.
Incubate things for a bit longer and so on.
Yeah.
But what about the activation energy of the transition state? What sort of things govern that?
So they found that specifically as the palladium metal approaches the arene here, and you have interactions between the sp2 carbon and the d orbitals of the palladium, more electron deficient arenes resulted in shorter bond lengths in these computational studies. So this is the crux of the stabilization effect via the electron deficient phosphine. Now, counteractive to this, the leaving of the hydrogen here is actually destabilized. That leaving of the hydrogen is stabilized more by electron-rich phosphines. So it's kind of an interplay here, and that's why my thoughts are that it would depend on application, where some applications would work better than others.
Right. Yeah. What about the phosphine part of that molecule? Does it play any role in apart from the indirect effect of,
yeah, so I think well, sterically it's important that the fullness of like the buried volume percent of this transition metal from the ligand, the higher buried volume percentage based on the fullness of the ligand would stabilize the reductive elimination step as well, just because you're able to relieve steric pressure by the leaving of the substrate. But then that works against your oxidative addition step now, where the larger your ligands are, the more difficult it is to do your oxidative addition.
Right. So that's more or less correct. In one of the papers, they talked about the fact that they looked at a series of different electron withdrawing ligands and found that there's actually a fairly large contribution to the activation energy that has to do with just the rearrangement of the positions of the atoms in the ligand, right? So when the transition state is formed, the phosphine rearranges it, goes, it has a change in its cone angle and all these sorts of things. And so I was wondering if you had thought about what effect the SF5 group might have on those sorts of things. Right. So there was one series that they looked at where in fact the more strongly electron withdrawing ligand had a rather poor catalytic behavior because the transition state energy was too high, and it was because there was a large steric component that was coming from the ligand itself, right? And so that started me thinking, well, what about SF5? It's this big bulky,
bigger,
bigger and so on. So just wondering if you had thought about that at all.
I did.
Might get in the way.
Yeah, I did, and my understanding at least is that I think that specific ligand was a 3,5 trifluoromethyl substituted pyridine ligand that had these two trifluoromethyl groups sticking out, and that they did have lower activity, even though that was the most electron deficient ligand out of the series they looked at. The sterics of this ligand did inhibit its activity as a catalyst. So I think that positioning the SF5 group at the 4 position here should help to alleviate those problems. If it was like I did mention, just out of completeness, a synthesis of a 3 substituted
Yep.
here. I don't think this would be a great I just kind of included it, but I think that this would
Sure.
actually be very bad as a ligand, just because it is now sticking out on the side, and you would increase that buried volume percent. Probably wouldn't be great. Also, the electronics don't work as well when you have it on this position.
Yeah,
But yeah, 4th position is the best, I think, because you want to avoid that kind of steric encumbrance.
that's right. So that
Yeah.
would allow you to at least to investigate that to see whether
Yeah,
that's a factor or not. So that probably would have been good to mention as well, that there are some issues there that could play a role. Just wanted to make a couple comments about your sort of the technical parts of the proposal related to budget and things like this. And the one thing that I think could have been a lot better is the HQP section. So you said you needed 2 PhD students, and then we'd have a series of undergrad students and so on. But nowhere in the proposal is actually spelled out what these students will be doing specifically with relation to the project, right? And so what I would have liked to have seen would be a description of a PhD project that fits into the larger program, right? And that doesn't have to be a lot, but just PhD student 1 will work on the synthesis of the 4-bromo sulfur pentafluoride, something along those lines, right? So just to divide it up and show that you've actually thought about what each person is going to do, and then how do the undergrads fit into that? So are they doing some kind of sub projects or providing starting materials or for the synthesis
specifically,
so that there's actually a proper plan there, rather than just the students are going to be trained in the lab.
Okay, yeah, that's true. Yeah.
What else did I have? Not a whole lot, actually. Oh yeah, so in the I think this is just a typo, but I don't know if you've got a copy of the abstract that you can show us.
Sorry, I just have to get my mouse here. From the proposal itself.
Yeah, so there were 2 documents, and one has the sort of common language abstract.
Sorry. No, where is it? Sent.
Yeah, it's actually the other one I was thinking of.
Oh, I know. Okay. The application form. Okay, here.
Yeah, so here, I was just wondering why, first of all, why did you write SF5 with the 5 not as a subscript? Is that because of some technical reasons?
Yeah, I couldn't, sorry, yeah, I couldn't get it to act as a subscript in the PDF application.
Yeah, okay, so that's fine, because of course that really should be
subscript.
As a subscript. And then what about it says the replacement of corrosive F2 and then CL something minus comma 2.
Yeah, I think that was also some sort of technical issue when I tried pasting it there. I didn't notice that, but yeah, I think it. I wrote out my application in Word, and then I tried copying it into the PDF, And I think
okay, but assuming that that was supposed to be Cl2,
Cl2, yeah.
do they use Cl2 in the traditional synthesis of SF5?
Yeah.
So in your reaction scheme, I didn't see any chlorine anywhere. It was just fluorine gas.
So it was actually an older Imamoto method in 2012. They used as a step one, they used chlorine gas
Okay.
here, and
Yeah.
now it's this cheap oxidizing agent, so it's much more clean and efficient.
Okay, so no, it's Cl2 and Kf, because I think on one of the slides it said F2.
Yeah, that was actually this one
So
here.
there is a one.
Sorry, let me just bring that up here. It was the Janssen procedure.
Okay.
Sorry, Philip procedure here, and it was only suitable for nitro-substituted diaryl disulfide. They use fluorine gas.
That was where my confusion came from. All right, so I think I'll leave it at that for this round, and I'll leave the rest of what I have for the next one.
Okay, thank you.
Thank you so much, Russ van der Es. Professor Nikonov, would you like to have some questions?
Well, yeah, I was going to abstain, but actually now I have a question. But before I do that, no d orbitals.
No d orbitals.
Josh, no d orbitals.
No d orbital. I agree.
I'm ashamed. You should have explained. Anyways.
Oh, I thought you meant for sulfur. Okay, yeah.
Yeah. So now my question. So you know me.
Mm-hmm.
How would I remove or destroy CF5? CF5. SF5. Sorry. Because you say it's on this. How did you put it? You're stuck with this. Yeah, that's what you said when you were answering Professor Mitalina's group. But you know, there is an older anecdote about. Gee, what's the name of the famous inventor, American inventor who invented Edison? Yeah. So guy came to Edison saying, "I invented universal solvent," and Edison asked him, "What does it dissolve?" He said, "It dissolves everything." And Edison said, "Go away." Because if your solvent dissolves everything, you cannot use it, right? So there is no glassware or whatever you will.
What are you holding it in?
You will use. So a functional group which is so useful, and then you're stuck with that. It's not useful functional group, so you have to destroy it or modify. So how would I destroy this group? Transform, make it more reactive, whatever.
Make it more reactive, yeah. To
get rid of it.
Get rid of it in some way. So it is susceptible to really strong base, like small, very powerful nucleophile. So like and butylithium would remove the SF5 group or decompose it in some way.
Yeah, but we don't know what happens, right?
Right.
So as one of my friends says, who is also Russian, but it shouldn't be very expensive. And funny enough, the hint of that was done by, it's in Science, by another Russian guy. So it looks like it's Russian thing.
A Russian solution to remove SF5.
Just think what we do. Right. Somebody who worked with you for a year or so did.
Irina.
No, not really.
Oh, okay.
That would be excellent.
Someone who worked with me did to cleave difficult. Oh, could you use like are you saying to use like low valent aluminum to activate?
No, that's too expensive.
No, too expensive. Okay.
Not so expensive. That's a rule.
Right. That is expensive. It's a cheap Russian method to remove SF5.
Relatively cheap.
Relatively cheap.
So that even organic people can do it on bench without glove box.
Okay. Do it on.
Well, think about modification of CF3. Or reduction of CF3. a science paper
a
about
science paper
10 years ago.
And it's something that's relatively cheap, and you could just do it on the bench. I'm assuming it's some sort of base because you'd want to like do a substitution.
Okay, hint, it's not base, it's acid.
Oh, it's acid.
Well, anyways, for the sake of time, you use silane as reducing reagent, and you use borane. And what happens is you generate silylamine, and silylamine comes after fluoride. So basically, you will start reducing sulfur by putting hydride equivalent. Obviously, hydride cannot support high oxidation state of sulfur, right? And at some point, it starts to pretty much self-reduce. So likely there will be HF elimination from sulfur, which again will come after silane. You will have to use excess of silane, and it will be most likely reduced to thiol.
To thiol, yeah. Yeah,
all the way down.
Silicon fluorine or silicon, yeah. Good.
So it was Ozirov's paper in Science.
Okay.
Which brought him ACS award, by the way, among other things.
Yeah.
So I really like all these things. It's good. It's just we need to learn. You need to learn, or we need to learn as community how to remove this group.
Yeah.
At the end.
Right.
Or change it into something else removable.
Sililium would work, I think.
Yeah. So well, that's my only question.
Thank you so much. So if everybody's good, we can move to the second round of questions. Does anybody need a break? Is everybody okay?
Oh yeah, just one comment. If this ever goes into patent, can I have my cut, please?
Yes. I'll take a quick break.
Okay, so let's have a couple of minutes.
Okay.
So let's give Josh. Let's come back at 5:30. Let's have 5 minutes break for Josh.
Thank you.
And then come back at 5:30. I know it's a little bit out of the schedule, but I think it's good. Give Josh a breather. Okay. So yeah, I'll give you 5 minutes, Josh, and then we'll come back at 5:30.
Sounds good.
Yeah. If you want to switch your cam off, Josh, you can. There you go. looks like Josh is back. Is everybody else good? Professor Metallinos, are you good?
Yep, I'm good.
Okay, then I think we can continue with Professor Metallinos. Everybody has about 10 minutes for the next round.
Okay.
Okay, thanks.
Thanks, Dr. Pilkington. I don't have too much more to ask. Just a few clarifications on some of your synthetic choices and in the proposal, some of which you have on your presentation as well. I think, I'm not sure what slide it is. Let's go to maybe 16, or actually that's a.
Oh, sorry.
The ligand synthesis. Yeah, let's look at the ligand synthesis there. Yeah, okay, it is 16. Yeah, so you discussed one way of making these particular ligands. This procedure here, we were using just a standard Grignard approach, get you to a point where you can just do a direct substitution. Actually, when you go back to the disulfide,
sure.
I believe it's the slide prior to this one.
Oh, here we go.
Yeah, right. It's okay. So you're going through bromobenzene, right? You're using bromobenzene there, and you're doing a standard sulfonylation reaction, and then you reduce that all the way to the thiol. So, and then of course oxidative coupling. Is there a way you can get to the thiol more directly than that?
To the thiol instead of
not necessarily from bromobenzene.
Like if you started with thiol and then did like a electrophilic aromatic substitution.
Of what, bromine, you mean?
Yeah. So like with N-bromosuccinimide, or do a bromination of the ring post like thiol.
Yeah, I mean that's one option. Yeah, I mean that I don't know what kind of selectivity you would get for ortho versus para.
Oh, it's true.
But that's one way, and that would be relatively inexpensive. What if you used para-dibromobenzene?
Para-dibromobenzene. As a brominating reagent.
What if you started with that instead of bromobenzene?
If you started with para-dibromobenzene and then did some sort of some sort of cleavage of that, with just like work up with like acid or something to cleave the.
So I guess I'm just trying to find a way you can avoid the sulfonyl group and having to do a reduction. How can you put in sulfur directly? Do you know?
Oh, some sort of sulfonylation.
No, you don't need sulfonylation. How could you convert the dibromobenzene into a mononucleophile?
So yeah, you have dibromobenzene, right? Convert it into a mononucleophile, somehow cleave.
You already do that in a couple places with the bromide, right?
Oh. With like iodine, like as an oxidizer.
Yeah, or you're thinking in the opposite direction.
Instead of trying.
You want to make it into a nucleophile. Use it in a couple of other reactions for the ligand synthesis also. Once you have SF5, right, already in there, see what do you do? You have SF5 and bromine. What do you do with the bromide?
I turn into a Grignard. With magnesium. Oh, okay.
For example, right? For example, so if you have a dibromo instead, and you can convert that, to the Grignard or to the organoletene, depending on how you set it up, right? And then what? What could you add to that mixture to put sulfur in?
So that would give you sulfur, and it would be like some sort of electrophilic sulfur species, like a
think really simple.
Like SO2?
Even really simple.
Oh.
That's a wrong oxidation state.
Oh, right.
That would give you back to sulfonylation. You don't want that.
Right.
That would give you a
Right.
sulfinate. That would give you actually sulfinate derivative if you use SO2.
SO2.
Right?
Oh.
Don't want that.
No, I want to get to
Want just SH.
SH, just SH2, but could you use that?
No, that's acidic.
That's
That would give
acidic
you
now.
back. I would put a proton in the position of where the Grignard was. Really simple. Even simpler.
Even simpler. Oh, just elemental sulfur?
Yep.
Oh,
Yeah, elemental sulfur.
elemental sulfur.
Elemental
Okay.
sulfur, you work it up and you get the thiol. Yeah.
Oh, wow. Okay. Yeah.
Yeah. That's one way to make that.
Right.
Yeah. You might get a few other mixtures too, but it basically falls apart to give you that. And then of course you can do your oxidative coupling and you've got your disulfide.
Okay. Yeah.
Okay, just yeah. A couple of other questions. I know in your proposal, you don't have it on the slide, but in your proposal you're using isopropyl magnesium, right? Magnesium chloride coordinated to lithium chloride as another way.
Oh, yeah.
Taking your Grignard reagent, right,
Yep.
from bromide. What's the advantage of using that?
So I think with this one, they had it was like a transmethylation, like they use isopropyl, this isopropyl magnesium, and then they did like a zinc transmethylation, and then they were able to get their nucleophile easier and then do substitution
so this is
from
scheme
there.
4 of your proposal. You don't have that handy. It's on scheme 4, page 10 of
I
your
might be able to
proposal.
bring it up quickly here. It should be in the here, and then.
Right.
Okay,
So you've got that procedure similar to what you have on your slide, where you're using that particular reagent. Why would you use that one instead of just magnesium?
So I thought of using this one just because it's a little bit more I believe because it's such an electron poor aryl group. I think it worked better than just magnesium iodide.
Is that in the literature, that reaction?
Yeah, this one's in the literature. Yeah,
okay.
yeah. And they well, not for SF5 sorry, actually, yeah, no, it was SF5. It was SF5, but they didn't use it to make phosphine ligands.
Okay.
I think
So
they used it for something.
So step 1 to step 2, where they make the Grignard from that SF5 aryl derivative, is in the literature.
Yeah, yeah.
Okay. So the next step you said is not in the literature, right? Where you make the phosphine. Okay.
Right.
So you have zinc chloride there. Is it really necessary to use zinc chloride? Why is zinc chloride there? Why do you have to transmetallate? Why can't you just use
Why couldn't you just you could maybe just add that directly to your phosphenol chloride and get substitution. I included the zinc for the transmetallation step because I thought it would. I saw them use it in the paper, but I thought maybe it would stabilize some intermediate a bit better than the magnesium having a zinc transmetallation step first.
Which one do you think is more reactive?
I think the magnesium one might actually be more reactive.
Yeah, I would probably concur. Yeah, I think it's probably more reactive to go that way.
Right.
I don't know. Maybe I don't know if it's necessary. Is my point. I don't know.
It's true. Yeah.
Especially since those magnesium chloride, those Grignard reagents that are also coordinated to lithium chloride tend to be more like magnesiates chemically, which is more reactive than just a typical Grignard reagent. So that's another thing to consider. I don't know if you need to transmetallate at all.
You don't need it.
Yeah. Anyway, just a couple of those details. Dr. Vandrest already asked my questions about big picture of the application. One reaction that would have been nice to include, or at least propose, if not, if it's not even known in literature, would be reactions that are troublesome currently with the current ligands that are, deficient. Like you said, you would expect improvement, right? If all other things being equal, if you replace CF3, for example, with SF5. But what would be nice is if you show a reaction where you have that trend already and reaction results are poor in catalysis, then maybe SF5 could put it over the top and make it substantially better.
Right.
Something that you could have proposed along the lines of what Dr. Vandrest was getting at.
Okay.
So that would have bolstered things a little bit, I think. And outside of that, I don't know if I've got maybe one other question here. Oh yeah, let's talk about chirality for a second.
Sure.
Okay. So you have, as you were discussing, I think it was compound, I guess B on this on scheme 4, since we have on the page here. We also discussed it in your proposal on the slides, but in B or D that you have there, when you were also discussing it in your presentation, you discussed that as being asymmetric ligand. Do you really mean asymmetric ligand?
Oh, no, no. No, that's not. Sorry, I didn't mean to say. Maybe I misspoke. I didn't mean to call this one an asymmetric ligand.
Okay.
It is a polyphosphino ligand, and an alternative asymmetric equivalent would be E, which is a
binapple.
Yeah,
okay.
the binap would be the R asymmetric. Yeah.
Oh, okay. Because I was trying to figure out how you would make a chiral ligand B or D or something. But
no,
the ligand itself
yeah.
is not asymmetric; they're chiral, but you could use them for asymmetric transformation.
Oh, chiral. Yeah. Okay, sorry.
Just
Yeah,
to clarify,
chiral.
because you're discussing the ligand as asymmetric. Ligand itself is not. Well,
yeah, it's a very symmetric. Yeah, or at least
Homo
chiral.
chiral. You could use it for asymmetric transformations, hopefully.
Yes.
Right.
Yeah,
So the chirality that you're referring to. Okay, I was a little unclear on that, but it's more clear in the proposal because you're talking about binaptals. Okay. So that's fine. One other question, and I don't know if this is a general question, and maybe I'm just ignorant on this point, but you use phosphite as an electrophile in this scheme, well, at least from 3 to C, right, in this particular scheme, and you have a similar reaction to make tri-aerophosphines also in your presentation. In this particular reaction, or let's talk about phosphites in general, right? So this reaction is known, right? It works pretty well.
Yes.
Yeah. Equivalent phosphine, you can do triple substitution. That's kind of useful.
Yeah.
That's very nice.
Yeah.
But what about phosphites themselves? Like, are phosphites electron deficient ligands in their own right? Can you use them in place of these fancy arylated derivatives?
I don't think the adjacent oxygens would make these phosphites particularly electron deficient. I think if they would be maybe electron rich, if anything, just due to hyperconjugation from the lone pairs of the adjacent oxygens. I don't think they would be electron deficient.
Okay,
ligands.
well, let me maybe I'm trying to remember something in the back of my memory, which maybe you've seen before too as an inorganic chemist, that you can enlighten me on and remind me as well. And that is, what is the cone angle of aerophosphines versus phosphites, like triethyl phosphite?
Oh.
Is there a trend that you can relate between cone angle and electronics?
So, so we're comparing just like a triphenylphosphine to this like triethoxyphosphite.
Yeah.
I think the cone angle would be larger for the. Well, you have the additional, if you had the oxygen and then like a phenyl group after it, in the case of a phosphite, this would be a larger cone angle, just because you have that additional molecule between the phosphine and the aryl. So phosphites in general, I expect to have larger cone angles, just than the aryl, just like triaryl derivatives.
So larger than triaryl, you think?
Well, not this one. I wouldn't say this one specifically, just because it's like a triethoxy. This one would probably be smaller, but talking about like if you had like a benzoyl.
I mean phenoxy?
Yeah, phenoxy. Yeah, sorry. Yeah, if you had like a phenoxyphosphite, I think that would actually be a larger cone angle than just a triphenylphosphine.
Huh. I'm not sure that that's the case, but
that's not the case. Okay, maybe I'm wrong.
But I'm not sure either. That's why I'm asking you.
I'm speculating based on that additional oxygen, allowing for the aryls to spread out a bit more. But I understand that you gain there because you're separating your bulky groups more from the phosphine, so maybe you're pushing it back. So whereas the aryls may be a little bit closer and more spread out. But I don't know the exact. It's kind of I'm just kind of speculating on which one would be.
So I'm not sure which one either. So let's simplify it to this question then.
Okay.
Which is, what is the relationship you think of the cone angle? Let's say the cone angle goes from large to bigger to the what's the relationship between that and how nucleophilic the phosphine is towards coordination to a metal?
I believe as your cone angle gets bigger, your nucleophilicity will go down. Nucleophilicity will go down. I'm saying that because if you're burying your phosphine in a bunch of aryl groups, you're going to have difficulty difficulty in your effective nucleation, difficulty in acting as an effective nucleophile.
Okay.
I feel like I've not had that.
Okay, that's fine. Honestly, can't remember myself.
Okay, yeah.
Okay, so I'll just leave it at that. Maybe maybe you'll get a better, clearer answer from Dr. Lemaire and Dr. Nikonov. Okay, I'll pass it along for questions. I'm done.
Thank you. Professor Lemaire, would you like to ask your next set of questions?
Sure. Yeah, I don't have too much either. I was going to ask a few synthetic, but I think Dr. Medalinos covered that pretty well. I guess maybe one thing, your scheme 2 in your proposal, I don't know if it's not this one, is it? No. Yeah, that's the second reaction. What is, so you just have P there, right? So what is that?
Red phosphorus.
I know it's phosphorus, but
yeah.
what in what form?
Red phosphorus. Red phosphorus.
Oh, okay. Why? So what is red phosphorus, and why do you have to use that?
So using red phosphorus here as a reducing agent. You could also use triphenylphosphine or sodium hydride or any kind of powerful reducing agent. But I decided to use red phosphorus because the resultant phosphoric acid that's produced from this reaction, I expect it to be not be an issue in subsequent synthetic reactions. So that's why I chose to use phosphorus red here instead of using some other species.
Is there something special about red phosphorus? Like why couldn't you use what's the other common allotrope?
Black phosphorus and white, but I'm sure like black would be like the most common. So
I don't know. I was just curious about that. So yeah, I get it's a reducing agent, but
yeah,
it just seems kind of strange that of a choice of a. But now that you explained it, it makes sense to me. And then again, I didn't really look at this too closely, but the use of iodine. So you're doing a reduction, but you have an oxidizing agent there.
Yes.
I don't get what's going on with that.
So iodine in this step here, what's the point of iodine here, right? I saw it in the procedure for the conversion of the thiochloride to the thiol, orthophonol to the thiol. The
Seems
point
odd. Like it's almost like you could just skip right ahead to the last that disulfide.
Oh, from here.
I don't know. I don't understand the role of the I2 in that reduction.
Right.
But then I'm not an organic chemist, so
Yeah. Oh, I wasn't sure too. I didn't really see an explanation for the I2.
All right, well, that's okay.
Not too sure there. Sorry.
The other, I had another. I guess you talk a little bit about the donor ability of phosphines, and it's quantified it's been quantified using the Tolman electronic parameter. So, can you tell me a little bit more about that? So there's this nickel complex that you described, and you say that you use the frequency of the A1 mode. So what do you mean by that?
So basically, if we examine the IR of a carbonyl, ligand attached to a metal center, and very and examine this this specific like symmetric frequency or symmetric stretching frequency of the carbonyl in infrared. Then we'll get a specific absorption based on the strength of the carbon oxygen bond. And as we add electron density to the metal center, we increase our amount of pi back bonding to the antibonding orbital of the carbonyl, and we weaken that carbon oxygen bond, and that can be observed in that A1 stretching frequency of the carbonyl.
So how many carbonyl stretching, how many carbonyl absorptions do you expect for that particular nickel complex with it could be any old phosphine ligand attached to it?
For this specific
like
one,
how do you identify that? Like how do you?
So you would have a it's really just a linear molecule.
Linear molecule?
Or like carbon monoxide.
But what the nickel complex?
Oh, the nickel complex.
It's got 3 carbonyls, right, and 1 monodentate phosphine attached. So what's the geometry of that, and what's the? I don't want to put you on the spot.
Yeah, it's like so we have these three carbonyls and the tetrahedral structure of this specific complex. So we would expect we expect like a symmetric, so all of them coming out at the same time would be 1, and then an asymmetric for tetrahedral geometry. What are the asymmetric?
Well, the geometry is tetrahedral, but what is the symmetry of that molecule? Like
like I know the symmetry elements of the tetrahedral.
Just the point group of the tricarbonyl with a monodentate phosphine.
Is it D3H?
No.
No. Oh.
So there's a really simple way you can use group theory, right, to predict how many carbonyl bands in these simple molecules. And for a molecule like that, that's C3b symmetric, you would predict 2 carbonyl bands. So how do you know which one's the A1?
Which one's the A1?
There's an A1 and there's an E.
There's an E, degenerate. So you're gonna get two bands. We're saying that the I guess the
okay, I'm kind of putting. I don't think this question's too fair. It's the 2 bands are very close together.
Yeah.
And the A1 band is totally symmetric.
Right.
And it's higher energy.
Okay, it'd be higher energy.
Yeah. So you that's kind of technical stuff. That's not really that important. But what I wanted to ask was, if you had 2 different phosphines, so say you had like a trialkyl phosphine, and you had trifluorophosphine. Which one would you expect to have the higher carbonyl stretching frequency?
Give me a sec here, but you would expect which one would you expect to have the higher like the higher A1? Yeah, so you would the trichlorophosphine would have I believe that would give you a higher carbonyl stretching frequency.
Yeah. Can you explain that just briefly?
Yes. So you have these halogens attached to phosphine. You're creating a very more electron withdrawing kind of phosphine ligand. So you would then be kind of siphoning off electron density from the metal then you would, as a result, have less electron density on the metal to back bond to your carbonyl, and then you would have a weaker. Oh, yeah, sorry, less back bonding to the carbonyl means a stronger, right? A stronger carbon-oxygen triple bond, and that would then result in a higher frequency, higher energy in that bond, higher stretching frequency. Yeah.
Good. And then you mentioned that for bidentate phosphines, you can do the same kind of analysis, but I don't know if that's true. Did you find that in a reference somewhere, or?
No, I maybe assumed that you could.
Okay, no, you can't do it because the symmetry is different, right? Like if you have a bidentate phosphine, you only have 2 carbonyls. The point group changes, and the number of carbonyl stretching carbonyl bands is different. So there's another way to do it for bidentate. I forget what it is, but there's another type of complex that's used there. So anyway, that's good. That's right. I'm good for questions. Right. Thank you, Josh.
Thank you. Yeah.
Thank you very much, Professor Lemaire. Professor van der Est, would you like to ask yours?
Sure. So I just have a couple of really quick things. I'm really proud of the fact that I can actually answer Martin Lemaire's question about the chemistry with the red phosphorus and the iodine.
Oh.
So what's going on there is that's in situ formation of PI3, and the PI3 is the reducing agent actually.
Oh, okay.
And PI3 is unstable, so that's just you can't really store it and so on. So it's just a way of producing it in situ.
Okay. And it wouldn't work with different allotropes.
I'm not sure about the allotropes. Probably the red phosphorus is easier to handle or something like that. Okay. I don't really know. Okay. So I just have a couple of really short things here just to finish up. Can you put up I think it's slide 5, where you were talking about the initial just sort of physical chemical properties? Yeah. So I was just wondering what the density there actually refers to, and why is the density higher for SF5? Like, is that the phenyl SF5 or what? Yeah. Okay. So why is the density there higher?
So it is a more closely packed molecule, and I guess in terms of you have these additional fluorines, and the trade-off for the increase in you have an increase in the van der Waal radii for sure because you have more fluorines, but it doesn't increase that as much as it does the molecular weight of the molecule just by adding the extra atoms. So you do end up with a net gain in density just because although your volume is increasing, the weight of the molecule is increasing more.
Yeah. So it's actually just the molecular. So the molar density actually of the molecule is lower. I did the.
Oh, okay.
Struck me as a bit odd there, and so I took you just take the molecular weight and divide it by, right, or divide these numbers by the molecular weight to get the molar density, and it turns out that the molar density is actually higher for the CF3 one, which makes sense because it's a smaller molecule and can pack more.
Pack better. Okay.
All right, so that was just the one thing I wanted to clear up. The other one was in your proposal, you said you wanted to do some DFT calculations and wanted to do a natural bond orbital analysis. So what I wanted to know is what's a natural bond orbital?
So you have your linear combination of atomic orbitals that you can use. So computationally, you can examine these linear combination of atomic orbital functions, and you can combine them to create molecular orbitals, and then from you can also look at lone pair orbitals and basically develop based on the wave function of the molecular orbital, you can kind of determine where electron density is distributed throughout the molecule, and it's just a way of modeling electron density, like in terms of
Sort of. So there are different types of natural orbitals. Do you know the distinction between them?
I remember I saw it, but I don't remember right now off the top of my head. But yeah, there's four specific ones that I remember seeing.
There's natural orbitals and
there's one that refers to like lone pairs, I believe, and then there's one that refers to like bonding orbitals.
Yeah, not so much.
Not so much. Oh.
So the natural orbitals are just you know, for a certain number of electrons. So you can have 1 electron natural orbitals or 2 electron natural orbitals and so on, in which you effectively project out portions of the n-electron density for either electron pairs or for single electrons and so on. And so the bond orbitals are the electron pair ones, right? And that also will project out lone pairs in the molecule. And so what you can see, it kind of creates a picture of the density that allows you to see what the bonding in sort of a Lewis picture or valence bond picture looks like.
Yeah, I did read a really interesting paper on like the hypervalency of SF5, and they used natural bond order analysis to kind of disprove or maybe not disprove, but more accurately define the bonding situation in SF5, and the natural bond order analysis really helped explain that it's not necessarily an expanded octet. It is still like an sp3 hybridized sulfur, just with a +2 or between +2 and +3 formal charge. Yeah. And yeah, sorry, I couldn't answer that one, but yeah.
No, that's fine. Yeah, and then I guess the final thing is, if you're going to do some DFT calculations, have you thought about what resources you would need for that? Because it's not mentioned anywhere in the proposal, right?
Right. So I've tried some work here with Orca, just in modeling like some basic molecules. But yeah, I would need Orca, then with some server time, to run any kind of calculations.
And so would that cost you anything? Would you should there be a budget item for that in your proposal?
I wasn't thinking of making it a major part of the proposal, so I was thinking I could just use the free server time that I get with like having an Orca account, and since it's not a major component, I could just wait for computational time there. I didn't really think I would need to invest budget into it. Yeah.
Sure, would probably have been better to mention something like SharkNet that Brock is part of, where we all have. I mean, you have to write a little application and so on, but you can get an account on SharkNet and use the server without any cost to you. And then you have access not just to Orca, but to Gaussian and all sorts of other possible programs and so on. All right, so that's where I'm going to leave it for now.
Okay, thank you.
Thank you very much, Professor van der Est. Professor Nikonov, do you have any additional questions you'd like to ask?
No, I'm good. Yeah,
okay.
I'm just very happy that Professor van der Est could answer the question of Professor Lemaire, so I believe he passed.
Excellent. There's nothing like passing a candidacy exam. Cool. So, are there any other questions from any other members of the committee? Did they forget something, or they have anything else they would like to ask Josh? Everybody's good. And Josh, are you okay? Is there anything you want to ask?
No, thank you for your time.
You're okay?
Yep, all good.
Okay. Then if everybody's good, I'm going to ask you, Josh, to step out. I will invite you back in once the deliberations are finished.
Okay.
So if you could just step out, we can proceed.
Sorry, I'm just two computers I have to log off here.
No problem.
Where is it here? Okay.